Section 3.3, derivatives of the trig functions. This is a relatively short section because it really just requires that you know your derivatives of the trig functions. There's no fancy process here. This is straight memorization. If you're interested in why these are what they are, then you're welcome to look through this section in the book and see all the details about how we derive these. But once you have the sine and cosine derivatives, the other derivatives can really just be gotten using quotient rules mainly. All right, so it's the derivative of sine, derivative of cosine that make all the difference here. And like I said, the rest of them can be found because remember, each of those functions can be written in terms of sine and cosine. So now there's a couple of things to remember here, and I've mentioned this before. You've got to remember your basic trig. Right? You've got to know your basic trig identities, like the reciprocal and the ratio identities and the Pythagorean identities, those guys. And you also have to know your basic trig function values. So they go back and review the values for sine, cosine, and tangent of pi over 6, pi over 4, pi over 3, your quadrantal angles, all those guys. So go back and do a little review there because they do come up in the context of working with these functions. Right? So with that said, right, the derivative of our trig functions, the derivative of the sine function is the cosine function. Turns out that the derivative of sine is cosine. But the derivative of cosine is the opposite of or negative of the sine function. So obviously you got to keep those SIGNs straight. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of the secant function is the product of secant and tangent. So the derivative of secant is secant tan. The derivative of cosecant is negative cosecant cotan. So notice it's the co-functions, cosine, cotangent, cosecant, whose derivatives are negative. The other three are positive. Other than that, it's memorization. You have to know them. And so commit those to memory. Otherwise, we're following the same processes that we followed before, like product rule, quotient rule, sum, difference rule, those types of things, constant multiple rule. Everything is still the same, regardless of the type of function in terms of processes. So take, for example, I'll just run through a few examples with you just to point out a couple things to be careful of. So say number one, I've got the function f of x equals the product of x cubed times sine of x. So as we mentioned in that previous section, I have to recognize that I'm dealing with a product here, right? So yeah, I do see a trig function there, but even more so, the overall function f of x is a product of x cubed times sine x. So the first thing I'm doing is using our product rule to write out my derivative. What is f prime of x? It is the first times the derivative of the second plus the second times the derivative of the first. And then we go in and find each of those derivatives, derivative of sine, derivative of x cubed, and I rewrite. So then I've got x cubed times that derivative of sine, which we just said is cosine, plus sine times the derivative of x cubed, which is 3x squared. All right, so we go in and find each of those individual derivatives. Now once I'm done with that, the derivative is finished. All right, and the rest of it, anything you do from this point forward is just rewriting. So again, I would maybe just clean this up by rewriting the second part of this. I have x cubed times cosine x plus 3x squared times sine x. And I mentioned to y'all before, you may see a lot of factoring done with these. That's perfectly fine the way you have that written. I mean, if you even left it like this, I wouldn't dock you anything if you left it that way. I just think it looks a little bit better the second way. But you'll also see quite often the factoring done. Right, so the fact that both of those terms have an x squared as a factor, you can pull out the x squared and you're left with x cosine x plus 3 sine x. Right? So again, whether or not you do that, I'm not so particular about that, but you do see that done quite often when you look at your solutions. Okay? But I mean, that's it. So there's nothing more to it than that. It's really just a matter of you have to know your derivatives and then have to use it in the context of working with other processes. So number 2, I've got the function g of x equals 4 times secant x minus tan x. Again, pretty straightforward. Constant multiple rule still applies, right? 4 times the secant of x. The derivative of 4 secant x is 4 times the derivative of secant, right? So the constant doesn't affect your derivative. You could also, I just want to mention this again, kind of thinking about it. You look at this as a product. We kind of talked about it at the time that we mentioned this constant multiple rule. If you look at that as a product of 4 times secant of x and you follow the product rule, remember product rule says you take the first times the derivative of the second plus the second times the derivative of the first. But since the first is a constant, its derivative is 0. And so the second part of your product rule ends up being 0 anyway. So but I see people do it. It's like, okay, you maybe just don't recognize or kind of overlook the fact that that's nothing more than the constant times the function, and you can differentiate the function times the constant. Sometimes I see product rule used there. I mean, it's fine. You can use it. Just making it a little more work for yourself, but it's not incorrect. So then back to the basic process, since it's a constant multiple, so I'm going to take the 4 times the derivative of the secant function that we just said the derivative of secant is secant tan, so this is g prime. Derivative of the secant function is the product of secant and tangent, minus the derivative of the tangent function, which we said is secant squared. So again, that's just straightforward memorization, nothing more to it than that. Again, you could maybe, if you wanted to factor out a secant out of this thing and rewrite this as secant x times 4 tan x minus secant x, you could do it that way. But again, that's just doing some factoring. Whether or not you choose to do that is purely arbitrary on your part. I mean, there may be situations where we would choose to factor when we're trying to simplify a fraction or when we're solving equations and this type of thing, but we'll deal with that when that becomes necessary. But in terms of just finding the derivative, that's fine. Number 3, I've got y equals tan x minus 1 over secant of x, a nice quotient. And we've already mentioned with the quotients, you could use quotient rule here, or could I possibly rewrite the function into a different form and use a different process? So again, I'm going to do this in 2 different ways just to show you the difference. So let's go with quotient rule first, the way that it's written. So y prime, remember our quotient rule, low d high minus high d low over low squared. So here's our derivative y prime, low d high minus high d low over low squared. And then we go in and find each of our derivatives. The derivative of tangent of x minus 1. So here's y prime equals, wrong step, over here. So y prime equals, there's the secant x times the derivative of tan x minus 1. Derivative of tangent is secant squared. And then remember the derivative of 1, get back over there. The derivative of 1 is 0. All right, so that's our derivative of tan x minus 1, which would be secant squared minus 0, or just secant squared. Then we have the minus tan x minus 1 times the derivative of secant, which we said was the product of secant and tangent. Okay. So each one of those, I just found the derivative of tangent x minus 1, which is secant squared minus 0. And the derivative of secant, which is secant tan. And then all of that's still over that denominator squared, or secant squared in this case. Now again, I'm done with the derivative. That's it. The rest is all rewriting and putting our function into a more presentable form, simplifying it as much as possible. So first we just multiply everything out. So I've got the secant times secant squared up here. So that'll give us secant cubed. Second part, I've got this secant tangent times the tan x minus 1. I also have this negative right here. So I went ahead and I think I combined those. I'm trying to get rid of that. I'm combining those all into one step. So in other words, I need to multiply those two together and also the negative. So I've got that secant tan times tangent times that negative in front of that. So I've got negative secant tangent squared. Then I've got that secant tangent times the 1, which will give us secant tangent. Now, there's a negative here, there's a negative here, so the negative times negative makes that positive. So that's the positive 1 times secant tangent gives me plus secant tangent. But again, as I keep coming back to, that's just algebra. That's just distribution and multiplying. Watch your signs. And then all of that is over secant squared. That hasn't changed. Now, the next thing I did was, since every term in that numerator has a secant in it, I went ahead and factored out the secant, common factor. So that leaves me with secant squared minus tangent squared plus tangent, because I just factored a secant out of each one of these. There's 3 of them there, and then there's 1 there and 1 there. So factor out a secant, and I'm left with secant squared minus tan squared plus tangent. Again, still all over secant squared. And another reason I went ahead and factored out the secant is, notice I can simplify the fraction, because now I can divide out that secant in the numerator that I just factored out with one of these secants in the denominator. So that leaves me with the numerator, secant squared minus tan squared plus tan, all over secant. I'm able to divide out one of the secants. Now, the next thing I did, and this is where, I mentioned earlier, your basic trig identities. I see a secant squared and a tan squared. Remember, there's a Pythagorean identity there that says 1 plus tan squared is equal to secant squared. That's a Pythagorean identity. So notice I can take that and rewrite it and say that 1 then would be equal to secant squared minus tan squared. All right? It's not the calculus. It's the algebra. It's the trig. So I can take this secant squared minus tan squared here, and I can replace that with 1. That's an identity. Minus, or plus rather, the tangent, that's already there. So that's where that 1 came from. It was using Pythagorean identity, so I've got 1 plus tangent over secant. Now, again, this is perfectly fine in terms of a simplification, but I went ahead and did the next step just so when I do it the other way, I can show you that I did actually get the same result. So this is doing that next step what we've done before. I took the fraction that has multiple terms in the numerator, and I went ahead and broke it up. So 1 over secant plus tangent over secant. Now remember, 1 over secant is cosine, right? That's our reciprocal identity. And then I rewrote tangent as sine over cosine, and I rewrote the secant as 1 over cosine, because notice I could then simplify sine over cosine times the reciprocal times cosine. That'll leave us with just sine. And so after all is said and done, all right, and I do all the simplification here, let me maybe write this because I skipped that step. This would be sine over cosine times the reciprocal, right? Cosine over 1. And then you can divide out that cosine, you're left with sine. So that leaves me with cosine plus sine as the final version of our derivative, okay? Now here's the or, here's the optional process. Because remember I told you, if we can get around without having to do quotient rule, because that's what we did here, you're typically going to be better off. Now with the trig functions though, you do have to be a little careful because it does require some use of some trig identities. So let's take the tan x minus 1 over secant, right? That was our original function, y equals. And the first thing I did was rewrite that function. Get that out of the way. By first breaking up that fraction. Right? So I rewrote it as tan x over secant x minus 1 over secant x. Right? That same little process we keep using with the fractions. And then I simplified each. Now notice that's the tan x over secant x. It's similar to what we just looked at in that previous version of this, to where the tan x can be written as sine over cosine. Secant is 1 over cosine. Right? So that's what we had done right here. And I multiply by the reciprocal, and I'm left with sine. And then the second part was 1 over secant, which is cosine. So ultimately then, this is what I get when I rewrite the function. Now I didn't do the derivative yet. I simply rewrote the function. So I took the tan x minus 1 over secant, I split it up. Tan x over secant minus 1 over secant. I simplified the tan x over secant by first writing that as sine over cosine over 1 over cosine. Multiply by the reciprocal, and you're left with sine. And then the 1 over secant is cosine. Now that's just rewriting the function. That is still y. That's our function. Then we find our derivative from there. And notice by rewriting the function this way, the derivative now is pretty simple. Because now I've got the derivative of sine, which is cosine. So y prime, the derivative of sine is cosine, minus the derivative of cosine, which is negative sine, or opposite of sine. Excuse me. And then I just rewrote that as cosine plus sine. And notice that's the same thing that we got up here when we did it the first time, when we went through that whole quotient rule up there. We got cosine plus sine. I got cosine plus sine here. But it was a lot easier because I did all the rewriting first. Okay? So that's, again, another case where, just depending upon how you choose to write the function, right, the derivative may be easier to find if you write the function into a simpler form. And a lot of times that can happen with these trig functions because of our identities and all of that we have that we can use to rewrite these guys. Number 4, y equals sine x over x squared. Just to give us an example of a quotient rule there again, but maybe with one that's not as ugly as the previous. But I also want to show you something else here too. So here's number 4, our original function, y equals sine x over x squared. Now remember I said, like in that previous section, you could choose to write that as sine x times x to the negative 2 and use product rule if you prefer. Right? Then you have to deal with the negative exponents. That's the only drawback of doing it that way. But here I'm just going to go ahead and do quotient rule. Again, because, I mean, it's not really that complicated of a function. You know, there's not a whole lot going on there. So the quotient rule here should not be too difficult either. So here's our quotient rule, y prime, low d high minus high d low. So low d high minus high d low over low squared. Now again, a good time to mention this, remind you, like I've said before, if you can bypass this, you know, if you don't have to write it out that way, if you can go straight from here down to there where you actually find the derivatives, that's fine. You know, you don't have to write it out like I have it written with the ddx. If you can go straight to finding the derivative, no problem. Just make sure it's done correctly. Right? Like I've told you before, don't do too much in one step. That's always the problem that we run across here, is just trying to do too much at once. There's a lot of moving parts, and you can mess yourself up. So here's our first, low d high minus high d low over low squared. So there's our x squared. Derivative of sine is cosine, minus sine times the derivative of x squared, which is 2x, over x squared squared, which would give me x to the 4th. Right? And then I could simplify. I could factor out an x. There is a common factor of x in that numerator, so I pull out the x. I'm left with x cosine x minus 2 sine x, and we can divide out that x with one of the x's in our denominator, and I'm left with y prime as x cosine x minus 2 sine x over x cubed. And there is our derivative. Okay. So not too complicated there, but again, we're always looking for simplification whenever we can. Right, and that's pretty much it for the trig functions. I do want to mention these two for you. Not that I'm not gonna ask you to deal with any of this on a test, but there are going to be a couple of situations where you see these limits come up. So I want you to at least be familiar with them, okay? So that when we do mention them, we'll say, oh, remember we mentioned these in our notes in section 3.3. So these are two limits. It's the limit as theta approaches 0 of the sine of theta over theta. Because notice, if you try to use direct substitution, theta in the denominator, our denominator is 0. Also, if you plug 0 in place of theta in the sine function, what's the sine of 0? The sine of 0 is 0. So it gives you one of those 0 over 0 situations, which we said is problematic. So we're just giving you this. We could do a whole table of values and go through that whole process. We could look at the graph, et cetera, et cetera. So we're just giving you the value of these limits at this point. Again, if you're interested in why this is what it is, you can look in the section and read through that. And I'm telling you that the limit as theta approaches 0 of sine theta over theta equals 1. Similarly, there's a limit for our cosine function. The limit as theta approaches 0 of cosine theta minus 1 over theta equals 0. Now notice in this case, if you plug 0 in place of theta, again, you have a 0 denominator. 0 into your cosine function, cosine of 0 is 1. And so again, I get 1 minus 1 or 0. That's a 0 over 0 situation. But notice on the left, I get 1. On the right, I get 0. So that's that little case. We mentioned it early on. We talked about limits, and I tell you, we're going to talk about that in a lot more detail later. That'll be in chapter 4. We'll have to deal with this. It's 0 over 0 in both cases, but in these two cases, I get two different results. Okay. But again, we'll talk about this later. So a couple of examples just to show you how this works with the, I did a couple examples with the sine function. So evaluating the limit as x approaches 0 of sine 5x over x. And kind of the trick with these is you want to see the argument of the function and the denominator of the fraction as the same. Because basically that's what the limit tells us. As long as that argument and that denominator are the same, then the value of this limit is 1. Right? And the same thing is true with the cosine as well. So sine of 5x over x. Well, I can rewrite that so that I have the same denominator as the argument. I can turn x into 5x by multiplying it by 5. But of course, I can't just multiply the denominator without also multiplying the numerator. So here's kind of the trick here. I took the original fraction, sine phi x over x. I multiplied it by 5 over 5. I'm just multiplying by 1. The reason I did that is so that now the argument of our trig function is the same as that denominator. And then this 5 is just a constant, right? So it's 5 times sine 5x over 5x, and that's our constant multiple rule for limits. The limit of a constant time a function is equal to the constant times the limit of the function. So I can just pull that 5 out. Now I've got the setup that I want. I've got the limit as x approaches 0 of 5x, sine 5x over 5x. As x approaches 0, what does 5x do? It also approaches 0. So it doesn't matter that I now have 5x instead of x there, as long as those are the same. Right? Because that approaches 0 as x approaches 0. But what then is the value of this thing? Well, it's 1 for the limit times that 5 that's in front of that, right? So there's the value of the limit, same as what we got up here. And then times that 5, that constant that's in the front. And so we get a value of 5 for this limit ultimately. Second one, a little bit more complicated, but same basic principle. I've got the limit as theta approaches 0 of sine of 2 theta over sine of 8 theta. Now again, don't do any stupid algebra stuff. and so, oh, yeah, I can divide out the 2 and the 8 and make that sine theta over sine 4 theta and all the craziness like that. Remember, 2 theta and 8 theta are the arguments of the sine function. Don't forget your basic algebra with all this, right? I can't divide out the theta, I can't divide out the sine, etc., etc. But I see all kind of weird math created with this stuff. So what I need to do is, again, turn that into something that I can apply the original limit, right? So I need sine of an argument over a denominator that are the same. So in this case, first thing I did was I multiplied each of the numerator and denominator by 1 over theta. So that I now have the limit as theta approaches 0 as sine 2 theta over theta over sine of 8 theta over theta. And then, to get the denominators the same in each case, I multiplied accordingly. In the first case, I multiplied by 2 to give me 2 theta in the denominator. So now each one of those is just like the first one that we did. So it's the limit as theta approaches 0 as sine 2 theta over theta. So I'll just multiply by 2 over 2 to turn that denominator into 2 theta so that it matches the argument. But then we also have the extra 2 that we just brought in. And likewise, in the denominator, I multiplied by 8 over 8 to give me the 8 theta in the denominator to match the 8 theta in the argument. But again, I have the extra 8 that we brought in right there. And then from there, it's the same process as what we did with the previous one, right? I went ahead and used some limit laws here just to bring that into play. So there's that constant multiple, the 2, that I pulled out, times the limit as theta approaches 0 as sine 2 theta over 2 theta, which we know is equal to 1. And then the bottom, the denominator, again, I pulled out the 8, limit as theta approaches 0, sine of 8 theta over 8 theta, which again, now that those are the same, is also equal to 1. So times each of the constants, 2 times 1, 8 times 1, 2/8 or 1/4. Okay. Again, I'm not something that I'm looking for test-wise, but we're going to see some situations where these pop up. I think there's a couple of homework questions where you actually have to try to make use of this, if you can figure them out. There's some tricky homework questions in this section. I expect that there's going to be some that you really can't figure out how to do or don't know how to do. And maybe we can talk about those when we do our review, our discussions. Okay? But yeah, at least be familiar with these two limits so that if we do have them pop up, we at least know what the heck they're talking about or why they are what they are. But that's it for that section. It's a pretty straightforward section. Just make sure you know the derivatives of your trig functions.